My name is Fabian. I head the Neural Intelligence Group at the University of Tübingen. Still, we will move to the University of Göttingen this summer, actually. I'm very excited to be here. Thanks for the invitation. I'm also very excited because this is not the usual crowd that we interact with. So we don't work with spiking neural networks or neuromorphic computing in my lab. But we are interested in something that I think is like you probably also share a lot of passion for, and that's the question like why or what makes brains and neurons, biological neurons, so much better at a lot of tasks than still state-of-the-art machine learning algorithms. And today I basically want to give you our perspective on this and a few results from a study we did recently. So when you look at the success of machine learning in the last 10 years now almost, and in particular in the successes of computer vision, deep learning is basically everywhere. So this plots the performance of the best performance on ImageNet, so 1 million image, 1,000 class benchmark data set in computer vision over the years. And you can see that basically there's a big, my mouse gone, there's a big jump in the beginning, and then the steady increase, and basically since 2012, this is the deep learning revolution. This is basically all the work of deep learning and the success of deep learning, basically. But even though these algorithms are really good at their respective data sets and also perform with superhuman ability on those data sets, they're actually surprisingly brittle when you look at how well they generalize beyond the statistics of their training set. And one example for that a very famous example for that are adversarial examples. For those who don't know what adversarial examples are, you can take a highly trained classifier, for instance, as a state-of-the-art network, performs really well on ImageNet, and can also faithfully classify this image like this as a cat. And then you find an adversarial perturbation, so that's it's kind of a noise that you optimize for that's invisible to humans because it's so small, so this is actually amplified here. You add that to the image, and that will completely throw off the classifier. So like now the cat becomes a moped, and the classifier is not simply unsure about what the image shows, but it's actually very certain that this image is a moped. So, and for us, obviously nothing has really changed in the image, we still see a cat. So that shows you already that these classifiers use different decision strategies compared to us. Another way of easily seeing this is if you add noise to your test images. So you can take, again, a highly trained classifier, you can add noise to the input images, and that will throw off the classifier. However, if you include the noise in the training set, then the classifier can learn this very well. So basically, if you add Gaussian noise and then during training and you test with Gaussian noise during test, again, the classifier is really good at it. So it's not a capacity issue. It's more like a statistical training set issue. But if you train on, say, Gaussian noise and then you test on uniform noise, then again, you're down to chance level, right? It's because the classifier overfits to the particular kind of noise. We obviously don't have that problem, and there's also a study that shows this. This is a study by Robert Garros et al. From 2018. So they used highly trained classifiers and humans and showed them particular test images and then distorted them with noise. And what you can see here is basically the performance across different noise levels of these classifiers in blue and humans in red. And you can see the classifier performance drops very quickly, whereas humans are way more robust. And this is not only true for this uniform noise, this is actually true across the board for a lot of image distortion. So basically what you should take...
hombre, Fabián.
Yeah.
Vale.
Onda que se ve un montón de bien.
¿Tú crees que tú puedes poner toda esa gráfica ahí? No se ve nada.
Is that for me or can you hear me?
No, please go ahead, Fabian. I think it's crosstalk.
What you should see is basically that the red curve is above the blue curve in all of these cases. So now the question is obviously how can we phrase how can we ask why the brain is still so much better than these deep network algorithms? And a very general way to look at this is to say that brains have a better inductive bias. So I basically inductive bias are like implicit assumption that every learning algorithm and every network comes with, and is also necessary for generalization. And I just want to basically clarify the concept with a simple toy example. So let's say you have some training data and as inputs and outputs to a linear regression problem, and you have a neural network that you want to train on. And let's say your neural network's a linear one, so all of what you can think of is linear functions. Then you will also get a linear function as a response, as a result of your training. And if your training statistic and your test statistic match nicely, then you get test data from exactly the same distribution. If it performs well on the training data, it should also perform well on the test data. So, but what happens if you move away a little bit from the statistics of your training data? So, for instance, when you add distortions to images, then the network needs to extrapolate. And then it depends a lot on what basically the internal assumptions are. If you have a linear network, in this case, it will again give this linear answer that it found on the training set, but that might not extrapolate so well. If you use a different kind of implicit assumptions, like this network has only sigmoidal functions, then it will obviously like for this constructed example, will extrapolate better. And so the difference in extrapolation, even they have basically seen the exact same training data, is in this implicit bias. So it's like what is built into this network, so it will pick one particular function over another particular function for a given training data. And in fact, you can show this no free lunch theorem that without any assumptions, you can also not generalize. So we actually need this good inductive bias, and we need these implicit assumptions. And why is that the case? So to basically intuitively how you can visualize it, if there's no inductive bias, if there's no assumptions, then the functions are basically like too powerful. So I just like want to depict this again with a simple toy example. So you have the blue points as training data, and we try to fit this with a 6-order polynomial. And the gray lines are basically different fits for different bootstraps of the data. And you can see that it fits the blue points, the training domain, really nicely. But once we move out of it, the functions are so powerful that they can basically do almost anything outside the training domain. However, if you bias your model, so you restrict the function class to, in this case, only 0 and 3rd order polynomial by construction, this is a good inductive bias for this data set, and then it will also generalize better. So it's all really about like, and that's the interesting part, is when we think about what we should, how I would like to think about what we should learn from the brain to improve machine learning is not to make it more powerful, but actually to make it more restrictive, because the networks are like artificial networks are already quite powerful. So what we need to learn from the brain is how to restrict them properly to generalize better. So how can we think about this kind of generalization? And one way to think about it is along David Marr's 3 levels of computation. So basically what he put forward as a way to describe computational systems. One is the computational level. So you could say, well, the brain is one neural network and it solves many tasks, all the tasks that we do every day. And maybe just by the fact that you have one network and that solves many tasks, that already restricts down the solutions that you can have to a learning problem such that it will generalize better. So maybe like one way to transfer this kind of knowledge would be to say, well, if you build a network that solves all the tasks that we solve at the same time, maybe that gives a good synergy between the problems, so we end up with functions that generalize better. Another way, so in the middle, is the representational level. So the brain has to represent data, sensory data, in one way or the other. And by doing that, it makes some algorithms easier and other algorithms harder. One example for David Marr's theory is if you can represent numbers in Roman numbers or in Arabic numbers, and depending what you pick, certain algorithms for multiplication or addition might be easier or a nightmare. So you could then try to basically match the brain on the representational level to force algorithms to represent your data in a way that somehow mimics the brain. And then the 3rd level would be the implementational level. So how is it actually implemented? And it's maybe the level that you would be most interested in is maybe by the fact that we use spiking neural networks, or that we have microcircuits or interneurons. Maybe that biases function in a way such that they generalize better. In the end, it might be a combination of all of those, and I try to depict this again here in this diagram at the bottom. So if you think about all possible functions that you could implement as this white box, then each restriction that we put on it will basically like restrict down this huge space of functions. So wide are all functions. Maybe by using convolutional networks, we get the gray circle. Maybe by finding a network that can solve multiple tasks at once, we get the intersection of the blue circles. By putting on biological architecture and neural data, we get more restrictions so that we end up with something in the end that has hopefully strong generalization. And we kind of know from the brain that this intersection should be non-empty, because the brain is a living proof of concept that there is an algorithm that can do all these things with these particular constraints. And what I will basically take like my last 9 minutes for is to talk about one project in the lab that we try to use approach this problem by trying to regularize artificial neural networks with brain data to match or get good inductive biases from a representational level. This is joint work with Andreas Tobias from Baylor College of Medicine, whose lab recorded the data. The data is from monkey V1, so primary visual cortex of macaque monkey. And the project was carried out mostly by a master student in the lab, Shad Zafarani, and 2 PhD students, Arne Nix and Konstantin Williger. So what's the idea? The idea is actually very simple. What we do is we train a network to solve a machine learning task, classification in this case. And then at the same time, we use the same network to predict neural data as well. And the idea is basically by forcing the network to solve both tasks at the same time, and it's particularly like predict neural data, we force it to be more brain-like and therefore regularize it towards like a more brain-like representation. And the hypothesis, and we call it the neural code training hypothesis, is that this will yield benefits in terms of extrapolation. Can we expect this to work? Yeah, there are other works, like some of them are also in collaboration with us, that basically show that if you match brain representations to network representation, you get benefits. So for instance, this is a collaboration again, or like a work from a postdoc in Andreas Tolia's lab, and they matched the basically representational similarity between mouse cortex and neural networks, and they could show that you get better against distortions from Gaussian noise, and you also get a bit better to distortions from adversarial images. There's another study that basically came out at the same time who showed that if you do representation matching between monkey and neural networks, you get more robust against label distortions when training classification networks. And work by Jim DiCarlo also showed that the other direction is also true. If you train networks to be robust against adversarial examples, you actually end up with a network that's better for predicting neural responses than comparable networks. So basically, the more robust, the better you are at predicting certain neural activity. So what did we do specifically? We took a VGG19, that's like one very famous computer vision architecture, and we trained it to predict to solve tiny ImageNet. It's a scaled down version of ImageNet, and we predicted neural activity from conv layer 3.1. That's a particular layer in the network that has been shown to predict neural activity well. And by that, basically, this bottom yellow block of the network is constrained by neural data and by classification data at the same time. How do we test whether we were successful in making a network generalize a bit better? We basically take the same approach as Robert Garros et al. So we take the images and then apply different noise distortions to it. So for instance, JPEG compression, or adding pixel noise, or adding like fake snow on it, and doing that with different levels of severity, and then test how quickly or not quickly the performance of the trained network deteriorates. And what's very important is that the network has never seen this kind of noise during training, so it could not have known about this noise from the training data. It only sees it at test time. Okay, so what do we get as results? So this is basically from left to right, our best result, our median result, and our worst result for the 3 different noise types. What you see in black is the baseline. That's a network just trained on clean images. And you can see that over different levels of corruption severity, the performance drops. And then red is the co-trained model. So one that has, where the bottom part has seen monkey data and the clean image data. And you can see that at least in the best case and in the median case, the network is more robust against this noise distortion because it declines slower. Then the question was like, how good could we be in general? Because we only share the bottom part of the network. So the top part only has seen clean natural images, so it can basically do anything at once and also like very non-robust things. So we try to come up with so-called oracle models that to get an idea how good we could have been just by the fact that we only share a bottom part. And how we did this is basically train the bottom part, but while showing it the noise as well. So it is allowed to cheat a little bit, and that's why we call it oracle and web model. So these are just for comparison to basically get an upper bound. And then we did also control, where we used, where we shuffled images against the neural responses and co-trained with that. And that's the pinkish line. And you can see basically that this doesn't yield any benefits. When we compare that across the different noise types, like we see that in many cases, we get an increased robustness. And when we basically accumulate the results over different noise types and different initialization seeds and severities. So basically we group the noise into, group the distortion into noise, blur, weather, which are more natural types of distortions, and digital. Then you can see that in most cases, all but the weather one, we get an improved robustness from the multitask learns from the co-trained model, whereas there's no benefit in the shuffled control as it should. And in many cases, we are actually close to our model is allowed to cheat, so to our oracle model. Then we looked at whether we can also find the similar result to what DiCarlo found. So remember, if we think that neural data should help to make the network more robust, then what we would expect is that the better we predict neural activity, the more robust we should also be. And this is basically what's shown in this plot here. So on the x-axis, you see the performance in predicting neural activity. And on the y-axis, you see the robustness score, and you see that they're positively correlated. That's not the only factor. There are other factors as well, like how good we're initially on the clean images. That's shown in the color. That's a factor as well, but basically both contribute, and we also find this correlation between model robustness and the ability to predict brain data. That's already it. So what I hope to show you today is like one way to look at why brains generalize better, and that's that they have a better inductive bias. And then basically put forward the idea that multitask learning can be an avenue to transfer inductive biases between actually measured neural data and artificial neural networks. And then as one application of this, I showed you like the project from the lab. It's co-training on monkey V1 data yields improved robustness of classification models to image distortions. And finally, like we basically find the complementary result to the Carlin lab is where they find that the more robust, the better for brain. We find the better for brain, the more robust. So there's a nice correlation in both directions. Yeah, and those are my funding for this project. And I thank you for your attention, and I'm happy to answer questions.